Okay, so I want you to imagine for a moment, you're a manufacturing engineer, you're on the shop floor, lights are humming, and you have just a massive headache.
And on your desk is an order for a lead screw?
And not just any screw,
Yeah.
right? We're not talking about something you'd find at the hardware store.
No, not at all. This
Yeah.
is the high-stakes stuff.
It has to be long, maybe 3 meters. It needs to be thin. And it's got to be incredibly precise because it's going into, I don't know, a surgical robot or the steering system of a high-end car.
Right.
So you do what you've always done. You grab a rod of high-grade steel, you load it onto a traditional lathe, and you hit go.
And that is exactly where the nightmare begins.
Almost immediately. Just disaster. You hear that awful screeching sound. The metal starts to heat up.
And because that rod is so long and thin, the heat has absolutely nowhere to go.
So the part expands, it bows in the middle, it literally turns into a banana.
It's the classic problem, thermal deformation. You are fighting physics. And, in a traditional setup, physics almost always wins. The part warps, the dimensions are shot, and you scrap it.
It's a total production disaster. You're burning through expensive tools, wasting steel, you're missing deadlines. But, and this is why we're here today, according to the research we've pulled specifically from the experts at J&M Machine Tools, there is a way out of this trap.
There is, but to solve it, you have to completely abandon how we normally think about cutting metal.
It involves a process with a name that, I've got to be honest, it sounds less like advanced metallurgy and more like a disco move.
You're talking about internal whirling.
Internal whirling. It sounds chaotic. It sounds messy. But the whole mission of this deep dive is to show that it's actually one of the most controlled, most precise methods for solving this impossible screw problem.
It's a really fascinating mix of, I'd say, brute force speed and just incredibly delicate geometry.
So let's get into the machine. If I walk onto that shop floor, am I just looking at a fancy lathe? Or is it a totally different animal?
You have to completely strip away your mental image of a lathe.
Okay.
I mean, in a standard setup, you have the workpiece, the metal rod, spinning really, really fast, and a stationary tool just gouges into it.
Peeling off layers, like you're peeling an apple, fast part, slow tool.
Internal whirling flips that script completely.
How so?
I want you to visualize a large steel ring, sort of a donut shape.
Okay, a donut.
But the cutting teeth aren't on the outside. They're mounted on the inner diameter of that ring.
So they're facing inward, like a very dangerous donut.
Exactly. Now, your workpiece, that long metal rod, it passes right through the center of that ring.
Right through the middle.
And that's why it's called internal. All the action is happening inside the ring.
I've got the visual, but I'm a little skeptical. If the ring just spins around the rod, aren't you just cutting a groove? How do you get a thread?
That is the first piece of the puzzle. You're right. If they were perfectly aligned, you'd just get a weird groove.
Right.
But the cutter ring is tilted. It's misaligned on purpose.
Tilted? How do you mean? Like just leaning?
They angle the entire ring to match the helix angle, that's the little gamma symbol in the diagrams, of the specific thread they want to cut.
So the cutter is attacking the rod at a slope. It has a specific wobble.
In a sense. But the real magic, the reason this whole thing works where lathes fail, is the speed differential. This is the big aha moment.
Okay.
That cutter ring, the one with the teeth inside. It is absolutely screaming. We are talking cutting speeds up to 400 meters per minute.
400 meters per minute. That's race car speed.
It's incredibly fast for a cutting tool. But here's the kicker. The workpiece itself, the rod, it's barely moving. It rotates at maybe, say, 20 to 50 RPM.
That seems completely mismatched. You've got one part doing 20 and the other doing the machining equivalent of 200.
And to make it even stranger, they usually rotate in the same direction.
Whoa, hang on. The same direction. Usually in machining, don't you want things crashing into each other to create force? If they're spinning the same way, aren't they just sort of running away from each other?
It does feel counterintuitive, I know, but it uses a principle that's closer to what we call climb milling. Because the ring is spinning so ridiculously fast and the part is so slow, the cutter just catches up to the material.
Okay.
So for every single slow rotation of that rod, the cutter ring moves forward by exactly one thread pitch.
So instead of peeling it layer by layer, pass after pass after pass.
It's carving the entire finished shape, the full depth of that thread, in one slow, continuous turn of the rod.
A single pass process.
Yeah.
You feed a raw rod in one end, a fully finished screw comes out the other.
That's it.
Okay, I buy the speed and I buy the efficiency. But I'm still stuck on the heat problem we started with.
The banana problem.
Banana problem, exactly. If I rub two pieces of metal together at 400 meters per minute, I don't care how precise it is, that's generating massive friction. Friction is heat. Physics says this thing should be glowing red and warping.
That is the most logical question to ask. High speed should equal high heat. But internal whirling, it sort of cheats thermodynamics. And it does it by changing the shape of the chip.
The chip, you mean the little scrap curl of metal?
Yes. In traditional turning, you get those long, stringy chips, right? The tool is buried in the metal 100% of the time.
Right. And the heat just soaks into the part.
It cooks the screw. But in internal whirling, remember that the ring is eccentric, it's off-center. This means that cutters aren't in constant contact. They enter, cut, and exit in a rhythm.
So they aren't buried in the cut.
Not at all. They swoop in, take a bite, and swoop out. And this creates a chip that's shaped like a comma.
A comma, like the punctuation mark.
Exactly. Starts thin, gets thick, ends thin. But the most important thing isn't the comma itself, it's what happens between the commas.
The gap.
The gap. It's called intermittent cutting. The tool cuts, hits air, cuts, hits air. That air time is the secret sauce.
It's a breather, a cooling break.
It is a cooling break. In that tiny fraction of a second, the tool cools down, but more importantly, the physics of that comma chip forces the heat to evacuate.
Evacuate where?
Into the chip itself. Metal takes time to conduct heat. If you cut fast enough and then immediately break contact, the heat gets trapped in that waste chip.
Wow.
The chip flies away hot, sometimes blue hot, but the workpiece itself never has time to absorb the energy.
That's actually really clever. You're using the trash, the waste product, as a heat sink to carry the problem away.
You got it. The chips fly away hot, but the workpiece stays cool.
And since it stays cool, it stays straight, no banana.
No banana, no thermal deformation. You can make that 3-meter-long screw, and it will come out perfectly straight.
So we've got speed, this natural cooling, single-pass efficiency. I mean, it sounds like the holy grail of manufacturing, which usually means there's a catch.
I love the skepticism.
Why isn't every thread in the world made this way?
You're right. There is no perfect process. Internal whirling has some very hard limits, and the biggest one is just, well, geometry.
Is this where Euclid gets his revenge?
Euclid always wins in the end. But look, first, the wins are huge. It's way more efficient than thread grinding. It removes a ton of material quickly, and it's tough. The research says it can handle materials up to 65 HRC.
Let's put that in context.
Sure.
65 HRC on the Rockwell scale is what?
That is extremely hard. We're talking hardened tool steel, the kind of stuff that would shatter a normal drill bit.
Okay, so it's strong. Where does it fail?
It fails at the angles. Remember we said you have to tilt the ring to match the thread angle?
The helix angle, the wobble.
Right. Well, just picture it. You have a rod going through a hole in a ring. You can only tilt that ring so far before the side of the ring physically crashes into the rod.
You run out of room, the donut hits the rod.
You got it. The hard limit is generally around 12 to 14 degrees.
14 degrees. That doesn't
Oh.
sound like very much.
It covers most standard transmission screws. But let's say you need a high lead screw, something with a really steep thread. That might need a 20 or 30 degree angle.
And internal whirling just can't do it.
Physically cannot do it.
Okay, I'm going to play devil's advocate here. Can't you just make the hole in the ring bigger? I mean, a wider donut hole gives you more room to tilt. Problem solved, right?
That's the classic armchair engineer solution.
Yeah.
And it's a trap. The experts at J&M specifically warn against this.
Why? What happens?
It all comes down to rigidity. If you make that hole bigger, you're moving the cutters further away from their support. The tool starts to act like a little diving board.
It gets wobbly.
It loses stiffness. So when that tool hits hard steel, it flexes. And that causes overcutting. The geometry of the thread just breaks down. You might get the angle you wanted, but the shape of the thread will be totally wrong.
And if the thread shape is sloppy, the part is useless.
Useless. So you're boxed in, you can't tilt more because you'll crash, and you can't widen the ring because of physics.
So if I need a 30-degree helix, I'm just out of luck.
With this method, yes. You're finding another way to make it, and it's probably going to be much, much slower.
That's a fascinating reminder that even our most advanced tech has these hard boundaries. But let's say I'm in that 13-degree sweet spot. Is it just buy the machine, press go, make money?
You would hope so. But there's a tooling trap that catches a lot of shops, and it usually comes down to trying to save a little bit of money.
The classic penny-wise, pound-foolish situation.
100%. The source material talks about a major problem where shops use conventional welded carbide heads.
Explain that. welded heads sound pretty sturdy.
Sturdy, maybe,
Okay.
but precise. No, imagine that cutter ring has, say, 8 cutting teeth on the inside. For this to work right, all 8 of those teeth need to be on the exact same center line.
And welding isn't that precise.
Welding involves heat, which causes expansion and contraction. It's almost impossible to weld 8 tips onto a ring and have them line up perfectly. So you end up with what the experts call spinning air.
Spinning air. That sounds poetic, but in manufacturing, I assume it's just bad news.
It is terrible news. It means that maybe 1 or 2 of your 8 cutters are sticking out just a tiny bit further than the others.
So those 2 are doing all the work.
Correct. As the ring spins, those 2 cutters hit the metal. The other 6, they're just spinning through the air, completely missing the workpiece.
So you paid for an 8-cutter system, but you're running a 2-cutter system.
And you're wondering why your tools are wearing out 8 times faster than the brochure said.
And I bet the finish on the part looks awful, too.
Jagged. You get tool marks everywhere because the load isn't distributed.
So what's the solution? If you can't weld them, how do you hold them?
You have to use machine-clamped whirling cutters.
Which means?
It means the ring has these precision machined pockets. You just drop a replaceable insert into the pocket and clamp it down. The pocket itself guarantees the alignment.
So the pocket forces them all to line up perfectly.
Exactly. All 8 cutters hit the metal at the exact same depth. You get a smooth, mirror-like finish, and your tool life goes through the roof.
And this lets you use better materials, right?
Yeah.
You mentioned cutting that super hard 65 HRC steel.
Yes. With clamp systems, you can use advanced inserts like CBN, that's cubic boron, nitride, or ceramics. Those are what you need to cut hardened steel without shattering.
So the lesson is, don't buy a Ferrari and put cheap, crooked tires on it.
That is a perfect analogy. The machine is the Ferrari. The cutters are the tires.
Okay, let's bring this down to ground level. Where am I actually seeing these parts? You said it's not for the bolts I'm buying for my deck.
No, definitely not. This is for high-value, critical motion components. The bread and butter are things like ball screws and feed screws.
The screws inside other machines.
Yes. If you look at a CNC machine or a robot arm, they all need to move parts back and forth with incredible precision. They use these massive long screws to turn rotation into linear motion.
Is there anything closer to home, though?
Do you drive a car?
I do.
Then you probably use internal whirling every day. Electric power steering or EPS.
The thing that makes the wheel easy to turn.
Exactly. Inside that steering column is a worm gear. That gear needs to be durable, mass-produced, and incredibly smooth so your steering feels good.
And this process can just crank those out.
It's the industry standard for EPS worms. It's also huge in plastics for making extrusion screws.
What are those?
Imagine a giant screw, maybe 10 feet long, that pushes molten plastic through a mold to make, well, everything. PVC pipes, toys, bottles.
Right.
Those screws are long, and they're under immense pressure. If you tried to turn them on a lathe, they'd warp from the heat instantly. Internal whirling keeps them straight.
But let's go back to the limits one last time. Is there anything else to just cannot do besides the steep angles?
There is one weird, almost plumbing problem. It can't handle large lead threads if the spacing is too wide.
Why? Geometry again.
It's actually about chip flow. Remember our Comet chips?
A little heat sinks.
Right. If the thread is really big, those chips get really big, the volume just becomes massive, and that cutter ring is a confined space. It's a closed donut.
So if you generate too much trash too fast,
The chips can't get out. They just pile up inside the ring.
they clog it.
They clog it like a drain blockage. If the chips can't clear, they get recut, they ruin the surface, or they jam the whole machine.
It's fascinating that in high-tech engineering, sometimes the problem isn't the computer code. It's just taking out the trash.
It often is. Physics doesn't care how advanced your software is if the machine is full of scrap.
So, to wrap this all up, internal whirling is a specialized superhero. It swoops in when the part is too long, the metal is too hard, or the precision is just too high for a normal lathe.
It is the champion of the single pass. It balances that terrifying speed with the smart physics of intermittent cooling.
And for me, the big takeaway is that idea of the Comet chip. We always think efficiency means more power or go faster, but here the efficiency actually comes from the empty space between the cuts.
Absolutely. It's about leveraging the physics of heat transfer instead of just fighting it with brute force.
But I also want to leave the listener with that thought about the 14-degree limit. We live in a world where we think tech can solve everything. We want the steeper angle and the high speed and the perfect finish.
But even the most advanced engineering hits a wall when it runs into simple geometry?
Exactly. You can't just make the hole bigger without ruining the profile. It makes you wonder, where else in our lives are we trying to force a steeper angle than a system can actually handle?
That's a very good question. Sometimes you just have to respect the constraints.
Something to think about next time you turn the steering wheel of your car. Thanks for listening to this deep dive.
Thanks for having me.
We'll catch you on the next one.